So we know that we have a video, we've applied feature detection, and we've tracked features through this video. And so we essentially have these sets of corresponding points given to us and the image coordinates of these points. We're going to take all of these image coordinates and organize them into a single matrix called the observation matrix. So let's take a look at the projection of points from 3D to 2D once again. And as we mentioned earlier, we are going to use the orthographic camera assumption. So let's take a look at orthographic projection. So assume that you have a point in the scene, which is P, and we are going to define a camera coordinate frame. In the past, we have placed the camera coordinate frame at the pinhole of the camera, if you remember, in image formation. But here we're going to say that the camera coordinate frame sits at one of the corners of the frame or the image. And let's say that its orientation, so that its position is given by the point C, and its orientation is defined by these two axes or unit vectors I and J, which are aligned with the two edges of the image plane. So now, orthographic projection tells us that you simply take the point P, which happens to be at the location XC, given by the vector XC, and you project the point P using a ray which is parallel to this optical axis right here, and that projection gives you the image point, and the image point has coordinates U, which has of course two components, U and V. So the projection of all points in the scene in this manner, using these rays that are parallel to the optical axis, is really what orthographic projection is. And so that projection is the following. You have the vector XC, you take its dot product with the unit vector I, you get U, the dot product with the unit vector J, you get V, and so that can be written as I transpose XC and J transpose XC. Now once again, perspective cameras can be approximated as orthographic cameras when the distance of the scene is great compared to the variation of depths within the scene itself. That is, we can assume that the magnification of all points in the scene is the same, and in fact doesn't even vary from one frame to the next as the camera moves through space. So that's the domain that we are in. So under that assumption, now we have these two equations, but that is in the camera's coordinate frame, this coordinate frame. The points we're looking for are defined in some world coordinate frame. So there's a world coordinate frame right here. We'll assume that it's at the point O, and now you have the position of the scene point P defined by the vector xw with respect to O, and we have the position of the camera C defined by the vector xw with respect to O, the world coordinate frame. So we can now express this vector xc in the world coordinate frame as follows. You can say xc is xw minus cw, and we can define the orientation of the camera given by the two axes I and j in the world coordinate with, again, unit vectors I and j. So you now have I transpose xw minus cw and j transpose xw minus cw. That gives you the image coordinates u and v. And that can be written as follows. I transpose the point P in 3D minus the point C, camera center, and the same for u right here. So these two expressions right here give us the orthographic projection of any point in the scene to the camera. You go from 3D to 2D. All right, so now we can restate the orthographic structure from motion problem as follows. You're given corresponding image points. These are 2D points, U, F, P, V, F, P. Again, F denotes the frame number, P denotes the scene point. And so we want to find the three-dimensional coordinates P of each point P. Those are the 3D points we're trying to recover. And then you have the camera positions CF in the equation of orthographic projection, And you have the camera orientations. The position and the orientation, of course, varies from frame to frame, image to image. Unfortunately for us, all of these are unknown to us. The only thing that we have at our disposal are the 2D image coordinates right here. So now we can write the expression for the image of a point. Let's take one point right here, P sub P, in camera frame F. We can write that as UFP again, VFP. You have IF and JF, which denote the orientation of that camera frame, and you have CF that denotes the center of that camera, and you have the point P. So those are your expressions for a point seen in a specific frame. And so what's known to us are all of these measurements that we have taken. Let's take our camera, we move it around, we get a whole bunch of these measurements after tracking each point. What we don't have are essentially all the unknowns on the right side. There's nothing on the right side that's known to us. What is of interest to us is, of course, P sub P, but unfortunately for us, we don't know CF or IF or JF. So how do we approach this problem? You can see why this is a really challenging, interesting problem. So first thing that we do is we remove one of these unknowns, which is CF. It turns out we can use a little trick to remove CF from these equations. So let's take a look at that trick. It's called the centering trick. Very simple insight here. So let's say you have your set of 3D points right here, and they project orthographically to the image to these points right here. We're going to assume that the origin of the world coordinate frame, which we are free to place anywhere we want, the origin of the world coordinate frame lies at the centroid of the scene points that we are trying to extract. So you take P sub P, and you take the average of all of those, you sum them all up, divide by n, so that's the centroid of your set of scene points that you're trying to recover. You don't know these, of course. That centroid, we will say, is the location of the world coordinate frame. That's equal to 0, the origin. So what this means is ultimately when we recover the 3D coordinates of all of these scene points, it will be with respect to this centroid right here. Okay, so now let's take a look at the centroid of a set of points measured in the image, the projection of the 3D points onto the image right here. So we'll call that the location of the centroid of all the points seen in any one frame F as U bar and V bar right here. So what is U bar? U bar is the average of all the U coordinates measured in that frame, that is over all the points, and that can be rewritten using the expression for orthographic projection we just derived as IF transpose times P sub P minus CF, remember the camera center right here, and that can be expanded into two summations, one over P sub P and the other over CF times IF transpose. Now, if you take a look at this one right here, which is the sum of all the scene points, that is equal to 0 because we have set our origin of the world coordinate frame at the centroid. So that goes away, and the sum of all of this divided by n is itself, because this is a constant. IF transpose CF is a constant. So you simply get minus IF transpose CF. So that is the U component of the centroid of the points measured in a single frame F. And then you get the V component similarly here. So what that says is that the U and V components of the centroid of your feature points is not a function of the locations of the scene points, P. It is independent of those. So that gives us a little bit of an insight, which is basically that it would be helpful to move shift the origin of the camera to the centroid. U bar, F bar. So we move this origin, this frame right here, to the centroid. Let's see that one once more. That's the shift of the origin. And now we're going to define all our image coordinates in this new coordinate frame. So this is what we'll call the centroid subtracted coordinates. We'll call those U tilde. U tilde is U minus U bar. And so you get this expression right here, which is I transpose P minus CF minus I transpose CF. So you see what happens here is by playing this little trick, you now have U tilde is equal to I transpose P, and CF is gone. And the same applies to V tilde as well, the other coordinate. So now we have the image coordinates of scene points, but you no longer have the camera center in the expression. You only have the camera orientation defined by the two vectors I and J. CF is gone. So that simplifies things for us. Camera location CF are now removed from the image formation orthographic projection equation. All right, so for now, for each point in a particular frame, you get these two expressions right here, which we have derived. The camera centers are no longer there. These can be written in vector form as follows. You have U tilde, V tilde, FP, that is frame F, point P, is equal to IF transpose, JF transpose. These are your two vectors, unit vectors that define the orientation of the camera for frame F, times P sub P, which is a 3D coordinate of the point P. That's for one point in one frame. And we know we have many points, we have N points, and we have F frames. So you can organize all of these expressions into a single expression using this matrix form, where all your measurements now sit right here. All your U values that you've measured for different points and different frames are stacked together as follows. And all the V measurements for different points, scene points, and different frames are right here. They're all centroid subtracted. Remember, when you measure these coordinates, you're going to remove the centroid for each one of these frames. That's how we arrived at this. And because we subtracted the centroid, on the right side you have the product of a matrix that has only the unit vectors corresponding to the orientations of the cameras in the F frames. Those are all the I and J vectors. So you have a stack of all the I vectors first and then all the J vectors for the F frames. And that we will call the camera motion matrix M. And then that's multiplied by the scene structure matrix S, which is the 3D coordinates of all the scene points. So you have your observation matrix right here on the left, which is W, which is a 2F times N matrix. 2F because you have F such equations, F such rows for U and F for V. So you have 2F times N, where N is the number of scene points. And then you have your motion matrix, which is 2F, again, twice the number of frames because you have I and J, times 3 because you have 3 components to each one of these vectors, I and J. And then you have your scene structure matrix S, which is 3 by N. 3 because you have 3 coordinates for each one of these points, and you have N such points. So that's your observation matrix. And the question that we're asking is, from this observation matrix on the left-hand side, can we recover the matrix S on the right side, which is your structure matrix? Well, it seems like if you can do that, obviously you've also computed the matrix M, which is your camera motion matrix. Indeed we can, because the observation matrix has some very special properties. We're going to exploit them in order to do exactly that.